So in this opener, again, we're just reviewing some of the exponent properties that we had done in 7.1. In the first warm-up problem, all those bases are being multiplied. When we have same bases being multiplied, we add those exponents together. So the 12 is coming from 4 plus 6 plus 2, and then the 16 is coming from the 7 and the 9 on the exponents for the y's. That middle opener, when we have exponents raise other exponents, we multiply those. So 4 times 7 is 28, 6 times 7 is 42. And then the last one, same basis being divided, we subtract those exponents. Remember that subtraction happens in the numerator. So it's 5 minus 3 in that numerator and 10 minus 15 in the numerator. So it's x squared times y to the negative fifth. And then that negative exponent is saying take that base and move it down to our denominator, and now the exponent can be positive. So x squared over y to the fifth there. All right. The reason that we're kind of starting with this is we're now going to do the same kind of operations, but with logs. Logs have very similar properties for us to be able to condense them down or expand them out. This gets really useful when we start solving equations that involve exponentials or logs, and it really helps us simplify some of the work that we'll have to do later on. The properties are very similar. And you're going to kind of see some connections with this. So the first property we're going to look at, and I think we had this exact same name on the exponent properties, is the product rule. What the product rule is saying is that if we take the log of a product, meaning two terms or multiple terms that are being multiplied, we're going to expand that out and add the logs together. So I want us to kind of write, and when we work with these log properties, we're going to go in both directions, meaning you're going to take a single log and we're going to work on expanding it out so that it becomes multiple logs. We will also reverse the process and take multiple logs that are expanded out and condense them down into a single log. So that's maybe the biggest difference from everything that we did with the exponent properties. So our explanation is logs of products. Remember that products are the results of multiplication. So answer, or let's just say multiplication. Okay, so log of products expand to logs being added together. Okay, and really all I'm trying to do there is just write some words to kind of explain what is going on with this individual property here. So the product is m times n, and then I expand that out, so this log base b of m plus log base b of n. I guess the other thing that we should make a connection about here is that the bases will never change when working with these properties. It's just that what we're taking the logs of. So bases stay the same. What we take the logs of is what's going to change. Okay, so log base m times n is log base b of m plus log base b of n. And again, that connection, right, when we had same bases that are being multiplied with exponentials, I added those exponents. So all these log rules are going to have similar connections to the exponent properties. Okay, and again, that's because these bases are being multiplied, kind of like m times n, and I add those exponents. Here we're adding the logs. So you've got one example right here that if I have log base 5 of 5 times 25, that's going to expand out where the base stays the same, log base 5 of 5, plus log base 5 of 25. Okay, so with each property, we have a few examples we can work through. Why don't I'll do like one and then have you all do the next two, and we'll just kind of do that back and forth as we work through these properties. So natural log of 8x. Two ways that we can write this. I want to continue to enforce the idea that when you see ln, that is the natural log, which is a log with a base e. So log base e of 8x. So you can expand this. If you leave it as natural log, which is mathematically the most correct way to do it, it'd be natural log of 8 plus natural log of x. If I work with it as log base e, which again, for what we're doing here as we're learning this is perfectly okay. That would be log base e of 8 plus log base e of x. The only other thing we're going to look to do is after we expand these out, if any of the logs can be evaluated, meaning they can equal a specific number, like what you just worked on, we're going to actually evaluate that number. In this case, natural log of 8, e to the power of what is 8? I have no idea, right? That's going to be some decimal. Okay, we actually need a calculator for that one. But if it works out to be a nice number, I want us evaluating that. So if you're taking logs of numbers, just see if it can't be evaluated. All right, I'm going to have you all do 2 and 3. Just expand them out. See if there's any places where you could evaluate. This should be like a 1-minute deal. All right. Let's see how we did here. So in part, or number 2, log base 4, and then our product here is x times y, so that expands to log base 4 of x plus log base 4 of y. With us taking logs of variables, neither of these can be evaluated. The only time we're going to be able to evaluate these is if we're taking the logs of numbers. Okay, so in this case, nothing can be evaluated. Now, number 3, I did a couple of different things here. I first just expanded it out without filling in that base. Remember, if there's no base, that is base 10. Okay, so I first can expand it out and just say log 100 plus log of x plus log of y. Or if I fill that base in and have this as base 10, which makes the evaluating a little bit easier to catch, it's log base 10 of 100 plus log base 10 of x plus log base 10 of y. Either of these are perfectly acceptable. The one extra thing that I'm asking you to do is that evaluation piece. So log base 10 of 100, now we're taking a log of a number. Okay, that is going to evaluate to whatever 10 to the power of what is 100, and that would be 2. So we are going to actually evaluate logs when applicable. Okay, so this, I'm looking for an answer that says 2 plus log base 10 of x plus log base 10 of y, or 2 plus log of x plus log of y. You don't need to add the base 10 in there. But I do want us catching that log of 100 evaluates to 2. Right, questions there? All right, well, let's move on to our next rule. And again, I think we had the exact same named rule with our exponent properties, the quotient rule. And it's just the opposite. So now if we're taking the log of a quotient being the result of division, we're going to subtract those logs when expanding them. Okay, so we're going to say logs of quotients, which are the result of division, they expand to logs being subtracted. Okay, and notice that it's numerator minus denominator. All right, and like I've said, this relates exactly back to some of the exponent properties. If we look at that third opener, where I had same bases being divided, so there's quotient there, I subtract those exponents. Okay, all these rules get derived from their corresponding exponential form. Okay, then we've got an example down here of just the expanding part. So log base 5 of 125 divided by 5 could expand to log base 5 of 125 minus log base 5 of 5. That's obviously going to equal a number. Okay, in this example, that evaluating of the numbers is not there. That when we're working through these, I will want us to actually evaluate those numbers. This is more gets at how the property is being applied. Okay, the last thing that I want us to kind of think about as we work through these is right now we're going in this direction where we're taking a single log and expanding it out. If we have time, we're going to actually reverse the process. Okay, and we're going to take an expanded log and condense it down. So after you have this written down, go ahead and flip this over. Once again, there's one example I'm going to do, and then ask you to do the other two within your groups. All right, so number 4, I see that I have a quotient of 2 different terms. So expanding this out, I need to subtract. So it's the numerator, log base 7 of 49. I should say 49, not 47. Minus log base 7 of z. Well, log base 7 of 49, if I'm taking a log of a number, that might be able to evaluate. So when I see this, I'm thinking to myself, 7 to the power of what is 49? 7 to the power of 2 is 49. So this whole log just simply equals 2. So this simplifies to 2 minus log base 7 of z. All right, 5 should be fairly straightforward. 6 is going to be a little tricky when you expand out 6. There are 1, 2, 3, 4 terms in that log. So when you expand it out, there should be 4 logs. Some will be added, some will be subtracted. See what you all kind of come up with there. But number 6, there will be 4 different logs that you have in your expanded out expression. All right. So 5, not much different than what I did in 4, just that there's no evaluation part. When I think of 3 to the power of what is 10, it's not any whole number. Okay, it's going to be what is that 10? If the answer is not any whole number, okay, positive or negative, then we'll just leave it as is. So log base 3 of 10 minus log base 3 of x. Now on 6, like I've already kind of given you a hint on, is there are 4 different things we're taking the logs of. Okay, the first thing that I deal with is the quotient part. So I'm taking log base 9 of 81 times x and subtracting that from log base 9 of y times z. Now, there's still more expanding that can be done here because now I'm taking the logs of products. So those logs can be further expanded where I add what those logs, what the product of the logs that we're taking. Okay, the one that gets really odd is the 2 terms that are in our denominator, the y and z. We are subtracting both of those logs. So the use of parentheses helps us keep track of that. So I say, okay, I'm subtracting these logs, but I know that log base 9 of y times z expands to log base 9 of y plus log base 9 of z. However, both of those are being subtracted. So if I distribute that negative, they both end up being negative. Okay, so when we get multiple terms like this, one thing that we'll pick up on is any term that is in the denominator when we expand out is going to be negative when we expand those logs. Okay, so the final simplified expanded log here, log base 9 of 81, that is 2. 9 to the power of 2 is 81. Log base 9 of x, that's positive. That x was in my numerator. Then the other 2 logs are negative because of those terms being in the denominator. Okay, so this is the one that will always be a little tricky there just because of multiple terms being in that denominator and thus having to be negative. Okay, questions here? All right, we're almost to a stopping point after these next 3. We'll probably just work on the other logs and then save kind of the tail end of this lesson for Friday. And that will actually be a fairly short day. All right, so the last property we have is the power rule. So if you think back to, again, the exponent properties, when I have an exponent raised to another exponent, I multiply those exponents. Well, that same idea kind of gets applied here, that if I take log base b of m to the power of a, really what we're doing is we're taking that exponent a and multiplying the entire log by the exponent. So what I like to say is the exponent becomes the coefficient and vice versa. Coefficient can become the exponent. Okay, so let's just make a note of that the exponent becomes the coefficient. And that kind of leads into that multiplication, right? The way we would read this is A times log base B of M. So there's multiplication there with that coefficient showing up in front of that log. And again, it works both ways. If I have a coefficient, that can move to become my exponent. All right, I'm going to do a couple of these here because of how we can think about number 8 here. But like number 7, first, let's just leave it as a natural log. So natural log of y to the power of 5. This 5 can become the coefficient, making the expanded version 5 times the natural log of y. The other thing that we could do here, especially as we're just getting the hang of what natural log is I can write it as log base e. So log base e of y to the power of 5. That 5 still becomes a coefficient, and so this could also be written as 5 log base e of y. Again, I accept either one. Probably more correct to say the natural log, but either one works here. Okay, number 8, there's a couple ways of how we can kind of deal with the expanded log here. The first thing that I am kind of noticing is I'm taking the log of y times z, which all is being taken to the power of 3. Remember that if I have multiple bases being multiplied, all raised to an exponent, I multiply those exponents, right? That's exactly what we did in this opening problem. Okay, x to the power of 4, y to the 6, I took this 7 and multiplied the exponents together. Well, if we start with that, that kind of gets at how this should expand out correctly. So the first thing I'm going to do, it got really dark, is the y and the z have exponents of 1. I'm going to multiply those exponents by 3. So this is really log of y cubed times z cubed. Well, that's a product, right? Y cubed times z cubed. So I need to expand this out by adding. And so this is log of y cubed plus log of z cubed. And so what ends up happening is the exponent of 3 gets applied to both logs here. So this is 3 log of y plus 3 log of z. And if you want to write base 10 in there so that you actually see a base, by all means do so. Okay, it doesn't make a difference to me. So let's say instead you decided, hey, I know that exponent can become the coefficient. The other thing that you could do here is just start by saying this is 3 times log of y times z. Well, from there, any way that we expand this out, this coefficient is going to follow. And so this would be 3 log of y plus 3 log of z. Okay, this is a better way to see why that 3 kind of follows. But if you want to move it to the coefficient, that's fine. Just every new log you write is going to have that same coefficient. And again, if you want to write the base 10, by all means do so. All right, everyone do number 9. Should be some evaluating there. And then we'll just stop there and get some practice expanding these out. Last one here, and then we'll just kind of do the practice part that falls on the next page. So I took the approach of I'm going to take this exponent and multiply each product's exponent by 5. So 64 to the power of 1 becomes 64 to the power of 5. Z to the power of 1 becomes z to the power of 5. Then I can expand this out by first adding the logs because I have a product here. So it's log base 4 of 64 to the power of 5 plus log base 4 of z to the power of 5. Then each exponent can become the coefficient, making this 5 log base 4 of 64 plus 5 log base 4 of z. Even better way to read this would be 5 times the log base 4 of 64. And the reason why I'm saying that's better is because log base 4 of 64 does evaluate, right? 4 to the power of what is 64? 4 to the power of 3. So this is really 5 times 3, which is 15. So the correct simplified expanded out log here is 15 plus 5 log base 4 of z. All right, these are not easy. And it's one of those things that you've heard me say with other concepts and skills we've done in here that without practice is not something that you can just hear or watch me do and figure it out all of a sudden. Okay, we need practice with it. So instead of flying through the rest of this, we have 1, 2, 3, 4, 5 other logs that you need to work through. There's one other property that we need to explain, and I'll show that with number 11. So I'll do 11 for us. And this actually comes back to an exponent property that shows up every now and again. So I'm looking at this cube root of x here, and the cube root of x, or just roots in general, can actually be written as exponents. Okay, so let's write, if I have the square root of x, that is equal to x to the 1/2 power. Hey, if I had, and that's, remember the square root, we don't usually write the 2 there, but if I took like the cube root, that 3 will show up. That would be x to the 1/3 power. Okay, if I had a 4th root of x, that'd be x to the 1/4 power. Okay, so in general, the nth root of x can be written as x to the power of 1 over n. So fractional exponents are really us just taking roots, okay, and whatever root of the denominator is. So for number 11, I'm going to actually start by rewriting the cube root as x to the 1/3. That way it has an exponent now and allows me to apply some of these properties. So that's ln of x to the 1/3 power divided by 6y to the 4th. Then I'm going to expand this out. First, kind of dealing with that quotient. So I'm going to have 2 logs being subtracted from one another. So natural log of x to the power of 1/3 minus the natural log of 6 y to the 4th. This still needs expanded, right? 6 times y to the 4th, that's a product. So I'm going to put parentheses here just to kind of keep that group together. I'm going to do two things here. I'm going to take this 1/3, make it my coefficient. So 1/3 natural log of x, and then minus, in parentheses, natural log of 6 plus the natural log of y to the 4th. I'm going to also move this 4 to become that coefficient. So this is 1/3 natural log of x minus natural log of 6 plus 4 natural log of y. And that is perfectly okay for me saying that that's expanded out correctly. Here's 2 other things you might see here. If I have 1/3 times natural log of x, well, that's really 2 fractions being multiplied together. So you might also see that as natural log of x divided by 3. That's the exact same thing as multiplying something by 1/3. Then you might also see this negative distributed, making it natural log of 6 minus 4 natural log of y. Okay, and again, you don't need to necessarily get to this point. I am okay with you all getting here, but just some other things to kind of pay attention to. I will warn us that these log properties, these expanding, are not easy. Okay, these are ones that are a little bit more complicated. Last thing I'll say, and I'll be quiet, and I'm just going to let you work, and then our warm-up will be us going through these when I see you all on Friday. Is 15, you need to factor. Okay, so factor the quadratics before you start there. With our time remaining, work with your groups, do your very best to try to come up with what you think is the expanded version here, and we'll check these when we come back on Friday. Okay, that's all we'll get through today, so no extra homework. We'll save that.